Greetings, this is Professor Roman. I want to discuss in a little bit more detail some material we've already covered in preparation for Chapter 3. Let's let F be a field and S a non-empty set. Then by the notation F to the power S, which I'll just read as Fs, we mean the set of all functions from S to F. If F is such a function, little f, the support of the function is the set of all elements in the domain that are mapped to a non-zero element in the codomain. And we'll let Fs naught be the set of all functions from S to F that have finite support. So these functions are non-zero only at a finite number of elements in their domain. Both of these, Fs and Fs naught, are vector spaces. Fs naught is in fact a subspace of Fs. It's not very difficult to find a basis for Fs naught. For each little s in the domain, we'll let chi sub s, this is the Greek letter chi, chi, be the function that sends s, little s, to 1 and everything else in the domain to 0. These are the analog of the standard basis vectors in Fn that have a single component equal to 1 and all the other components are 0. This set of characteristic functions is relatively easily seen to be a basis for Fs naught. Therefore, since there's one characteristic function for each element of the domain, the dimension of this vector space Fs naught is the cardinality of S. Let's take a closer look at these vector spaces, Fs and Fs naught. Ask yourself the question, what is the proper, most useful, infinite dimensional analog of the Euclidean type vector spaces Fn, where n is a natural number. So these are finite dimensional vector spaces. We might guess at first glance it should be Fs, where S is a set of cardinality k. K could be, or kappa rather. Kappa could be finite, in which case we get Fn, or it could be an infinite cardinal. In fact, since cardinal numbers are sets, perhaps we might guess that F kappa is the direct and most useful analog of Fn. But there's a problem when we consider the dimensions. We already know, of course, that the dimension of Fn is n, so an infinite dimensional analog of Fn, say kappa dimensional, we would expect to have dimension kappa. The theorem we are going to address in a minute tells us that the dimension of Fs is in fact greater than the cardinality of S. So in particular, F kappa has dimension greater than kappa. So perhaps it's not the best analog of Fn. On the other hand, Fs naught does have dimension equal to the cardinality of S. And so F kappa naught has dimension kappa, and perhaps that is the most useful analog of Fn, or generalization of Fn. Just to warm up to the theorem, let's consider first a special case. Let the field F be Z2, so that's 0, 1. Let S be the natural numbers, and so kappa is aleph naught, the first infinite cardinal, the smallest infinite cardinal. And so F kappa is this vector space of all functions from the natural numbers to 0 or 1, the binary functions on n. This set is in bijection with the power set of n. We can just, for any function from n to 0, 1, we can assign or associate the set of all natural numbers that are sent to 1. In other words, the support of the function. That's a subset of n. Any subset of n can function as the support of a function in F kappa here. But the power set of n has cardinality C, which is the power of the continuum, which we know to be strictly greater than aleph naught, which is the cardinality of the set n. Using this cardinality argument, we can prove that this vector space cannot have a countable basis, and so its dimension is greater than the cardinality of the set n. And to see that, suppose that we have a countable, linearly independent subset of this vector space. The linear span of I is the set of all linear combinations of vectors from I, but the scalars in this case are only 0 and 1, so a linear combination really boils down to a finite sum. Just take the terms whose coefficient is 1. So the span of I consists of all the finite sums of these vectors, and that is in that has cardinality equal to the cardinality of I. Okay. We did discuss a theorem early in the lecture series that while the power set of an infinite set, or any set in fact, has larger cardinality than the set, the collection of all finite subsets of an infinite set has the same cardinality as the infinite set. So I then spans a countable set of vectors, but the vector space is uncountable in size. So I does not span the whole space and therefore cannot be a basis. So the dimension of this space is bigger than aleph naught, which is the size of n. Now we can generalize this. Let F be a field and let S be a set of cardinality kappa. Then the dimension of Fs naught is the cardinality of S, which we have just said is kappa. And so if V is a vector space with basis B, then the dimension of fb naught is the cardinality of B, which is the dimension of V. Also, if kappa is an infinite cardinal, then the dimension of Fs is bigger than kappa. So let me add here, for example, let's say this is the dimension of Fs naught. So the dimension of Fs is strictly bigger than the dimension of Fs naught when S is an infinite set. If S is finite, of course, then all functions from S to F have finite support, so these actually are the same vector space, and obviously they have the same dimension. As to the proof, I remarked earlier that the characteristic functions form a basis for Fs naught, something not difficult to show. And so the dimension of Fs naught is the cardinality of S, which is kappa. As to the dimension of Fs, we must work considerably harder. So we begin by letting P be the prime subfield of F. We discussed the prime subfield of a field, I think it was chapter 0, an early lecture. It's the smallest subfield of F. When F has characteristic 0, it's a copy of the rational numbers. Of course, if F is a finite field, then its prime subfield is ZP, which is also finite, obviously. So in either case, the prime subfield of F is countable, and that is really why we need it. So the plan is to show this string of relations. The F dimension of Fs naught is equal to the P dimension of Ps naught, and that is less than the P dimension of Ps, which is less than or equal to the dimension, the F dimension of Fs. So what we've done is we've inserted the vector spaces over the prime subfield here. So this is sort of the meat of the issue here in this proof. If we can do what we want for the prime subfield, we can do it for any field. This first inequality follows from part 1 of the theorem. Each of these has dimension equal to the cardinality of S, and so they have the same dimension. For this center inequality, it's certainly clear that we have a non-strict inequality because Ps naught is a subspace of Ps, so it can't have larger dimension. But if equality were to hold, then both of these vector spaces would have bases of the same size, say, write it here. B is a basis for Ps naught, and C is a basis for Ps, and I've indexed them by the same index set because they're the same size. Then we can define a function, phi, between the two spaces by basically replacing fj by gj wherever you see it. This is a bijection from, in fact, it's linear, but that doesn't really matter. It's a bijection between the two vector spaces, and that means that the two vector spaces have the same cardinality, but that contradicts a theorem that we discussed briefly when we discussed cardinal numbers. It's theorem 8.5 in the book, which says that the cardinality of PS naught is strictly less than the cardinality of PS because P is countable. So we must in fact have strict inequality here. Now all we have to do is deal with this last one. But also an earlier theorem, 1.80, if you recall, I think it was under the heading field independence of linear independence. F is a field extension of its prime subfield, and so any linearly independent vectors in PS also belong to Fs, and they are also linearly independent in Fs. And since this applies to a basis for, this should be PS naught, then that basis is linearly independent in PS, and sorry, in, oh, my mistake, just PS. So that's correct. This applies to a basis for PS, which tells us, and so that basis is linearly independent in FS, which means the dimension of Fs is at least as big as the dimension of PS. And that's the final inequality. So that completes the proof. Okay. So the takeaway here for future is is this and is this. Okay. The dimension of Fs is strictly bigger than the dimension of Fs naught as long as S is infinite. And that should be relatively easy to remember, because if S is finite, then we don't need, then everything has finite support, and so these are equal. Okay. All right. So we have just seen then that if V is a vector space over F with basis B, then the vector spaces V and FB naught have the same dimension. Therefore, they are isomorphic. I'd like to find a nice isomorphism for FB. Something else we also discussed earlier is the restriction map. If you take a linear transformation from V to W and you restrict it to a basis B for V, you will get a function from B to W. It's no longer linear because B is not a vector space. Okay. The restriction of tau to B actually, because of the fundamental theorem on linear transformations, is essentially as good as the original linear map, because you just extend by linearity. The values of a linear map are completely determined by their restriction to a basis. So this is an injective map. And any such function from B to W can be extended to a linear map from V to W whose restriction is the function you started with. So in fact this map is surjective, it's an isomorphism. We talked about this before. And so the linear maps from V to W are isomorphic to the functions from B to W. And in particular, if W is the base field F for V, then the linear transformations from V to F, those are the linear functionals on V. The dual space of V, V star, is then isomorphic to FB. So, this is a summary. This is key information here, that FB naught is isomorphic to V, FB is isomorphic to V star, the dual space. We're going to have quite a bit more to say about the dual space in Chapter 3, and that's one reason why I wanted to do this now. Well, it follows then from our earlier information about the dimensions. We proved that if B is infinite, this dimension is less than this dimension, therefore the dimension of V is less than the dimension of V star. If B is finite, then these are the same. And so the V and V star have the same dimension. In any event, the dimension of V is less than or equal to the dimension of V star, and equal if and only if V is finite dimensional. This is a rather important result concerning the dual space. The space of linear functionals on V is at least as big as V. Now we're speaking dimension, not cardinality. Cardinality is not despite the previous theorem and one or two, or proof anyway, and one or two others, cardinality doesn't play a huge role in the study of vector spaces. There are occasions when it can produce results like we just saw, but for the most part, the size of a vector space refers to its dimension rather than its cardinality. So when I use the term size, I'm really referring to dimension. I'll try not to use it if I can help it. So the dual space has dimension bigger than or equal to the original space, and in fact equal precisely when V is finite dimensional. Now we can begin our look at Chapter 3, starting with a closer look at linear functionals and dual spaces. Here is the definition we've given much earlier in the book. A linear transformation F from V to its base field is called a linear functional, or simply a functional on V. The vector space of all linear functionals on V is denoted by V star and is called the dual space of V. And I will generally use lowercase Roman letters, F, G, H, and so on, for linear functionals. I think that's fairly commonplace. Maybe I should add, though, that I did not invent Roman letters. not quite that old. Couple of quick examples. The function that is on polynomials, that is evaluation at 0, is a linear functional. Also, the derivative at 0 is a linear functional. So are definite integrals on the space of continuous functions. Those are linear functionals. One of the interesting features of linear functionals is that all non-zero linear functionals are surjective. After all, the codomain F has dimension 1, and so the image of a linear functional, being a subspace of F, is either 0, the trivial space, in which case the function is the zero function, or it is all of F, in which case the functional is surjective. Also, if the dimension of V is at least 2, which is, of course, quite commonplace, then F cannot be injective because it can't be an isomorphism. The dimensions are wrong. And so, in summary, when the dimension of V is at least 2, all non-zero functionals are surjective, but none of them are injective. Actually, when V is finite dimensional, then the rank nullity theorem tells us that the dimension of the kernel of a linear functional is 1 less than the dimension of the whole space. So in rather loose terms, the kernel of a linear functional is very large. Here are some basic properties of linear functionals that are important to know. For any non-zero vector V in the vector space, there exists a linear functional on V that sends little v to a non-zero value. So accordingly, we can tell when a vector is 0, little v is 0, if and only if fv is 0 for all linear functionals. So the 0 vector is the only vector that is annihilated by every linear functional. We say annihilated, we mean sent to 0. If f is a linear functional on V, and if f of vector little v is non-zero, then the vector space can be decomposed into a direct sum of the one-dimensional subspace generated by V and the kernel of the functional. So a single vector V that is in the support of F, so it's sent to something non-zero, if you take that subspace, that one-dimensional subspace out, it's essentially disjoint to the kernel, and in fact the direct sum is all of V. So this is a very useful decomposition of V based on a linear functional. Of course, it has to be a non-zero linear functional in order to have this property. Finally, two linear functionals, f and g, have the same kernel if and only if they are scalar multiples of one another. I should say, non-zero scalar multiples of one another. Okay. So there's a non-zero scalar lambda such that f equals lambda g. As for the proof, part 1 follows from the fundamental theorem on linear transformations, and I'm going to leave the details to you. Part 2, to see first that the one-dimensional subspace spanned by V and the kernel of F are essentially disjoint, we observe that if W is in both these subspaces, then because W is in the subspace spanned by V, there's a scalar, say alpha, for which W equals alpha V. But because W is in the kernel of F, FW is 0, and so alpha FV is 0, FV is not 0 by assumption, so alpha is 0, which means W is 0. So the only thing in the intersection of these two subspaces is the 0 vector. To complete this part of the proof, that V is the direct sum of these two subspaces, we have to show that every vector W in V is a sum of a vector from the one-dimensional subspace and a vector from the kernel. Of course, all the vectors from the one-dimensional subspace are just scalar multiples of V. So what we need to do is write W as alpha V plus W minus alpha V and find an alpha for which the vector in the parentheses here is in the kernel of F. In other words, when you F annihilates this vector. Another way to say that is that FW minus alpha FV is 0, so that we can use this to solve for alpha. So the decomposition of W into a sum looks like this. So this is a direct sum. For the final part, of course, if F is a scalar multiple of G, where lambda is a non-zero scalar, then F and G have the same kernel. For the converse, suppose that the kernel of F and G are equal to, and we'll call it K. If we take a vector that's not in the kernel, then it's in the support of F or G and G. So we can decompose V this way. This is the kernel of F or the kernel of G. They're the same. F and lambda G will agree on K no matter what lambda is, because on K, F is 0 and G is 0. So we need only worry about finding a lambda for which F and lambda G agree on the vector little v. So FV equals lambda GV. Well, we just solved this for lambda. Now let's take a look at a very special class of linear functionals. Let V be a vector space, and let B be a basis for V. For each vector, V sub I, in this basis, we define a linear functional, Vi star, this is a common notation, by its action on the basis B. So Vi star applied to Vj is equal to delta Ij. This is for all j. Delta ij, as you may know, is the Kronecker delta function, defined this way. Delta ij is 1 when I equals j and 0 otherwise. The linear functionals vi star are called the dual vectors to the basis vectors vi. It's true that these are linear functionals, so it could be called dual linear functionals, but I've never heard that terminology. Dual vector is the common term here. It is, however, very important to keep in mind that despite the notation vi star, this linear functional depends not just on v sub I, but on the entire basis, because it is defined on the entire basis v. If you change any one of the basis vectors, it will affect all of the dual vectors. Here's an example. In F2, we have an ordered basis here. The dual vectors are simply defined as follows. V1 star takes V1 to 1, and it takes V2 to 0. And V2 star takes V1 to 0 and V2 to 1. Actually, we can describe the behavior of the dual vector vi star by saying that it picks out the coefficient of v sub I in any vector. An arbitrary vector, little v in v, is of course a linear combination of the basis vectors. So we can write something like this. V is A1 is AI VI, isolating that particular term in the linear combination. AI could be 0, but I want to make sure this term is present, plus a finite linear combination of other basis vectors. So J is a finite subset of the index set I. So any vector can be written in this form. Therefore, when we apply vi star to this, everything in this sum will be annihilated, because vi star applied to vj is 0 when j is different from I. The only term that survives is this first term, and so we get vi star of v is ai vi star of vi, and that's the Kronecker delta function. So this is 1, we just get ai. So applying vi star to any vector v picks out the coefficient of v sub I. There's another way we can express that. If we let, say, T be the subspace spanned by all the basis vectors except vi, then the vector space V is the direct sum of this one-dimensional subspace spanned by vi and this other subspace T. And then vi star is nothing but projection onto this one-dimensional subspace vi, spanned by vi, along this complement, this particular complement. So vi star is a projection map. I don't think it's commonly thought of that way, but it's another viewpoint. From the dual perspective, the vector vi picks out the coefficient of vi star in any linear combination of the dual vectors. And the argument is exactly the same. Here, any linear functional that's a linear combination of the dual vectors could be written this way. And again, AI could be 0, as could any of the coefficients, really. Then applying this to Vi, again, all these terms here go to 0, and the only thing that survives here is AI. So Vi and Vi star are both ways to pick out a particular component in a vector or a linear functional, respectively. If, as we've been discussing, B is a basis for V, then the set of all dual vectors, denoted by B star, does not need to be a basis for the dual space. And we'll see what's going on there in a minute. But it is easy to see that this set is linearly independent. Because if we take a linear combination of dual basis vectors, set it equal to 0, then by what we've just been discussing, f of Vj picks out the jth component, if you want, or the coefficient of Vj in this sum, in this linear combination, and that's Aj. So since f is 0, Aj is 0 for all j, and so the basis, the dual vectors are linearly independent. So of course that raises the question of do the dual vectors form a basis for V star, or if not always, when is that the case? Well, Theorem 217 tells us that the dimension of V is less than or equal to the dimension of V star, and equality holds if and only if V is finite dimensional. Well, remember that B star has the same cardinality as B. Just take the dual vectors. And so B star will be a basis for V star if and only if there is equality here. In other words, if and only if V is finite dimensional. When this is the case, when V is finite dimensional and the dual vectors form a basis for V star, we call that basis the dual basis for V star. How does one employ the dual basis for in the finite dimensional case, for a basis B? Well, we've already seen that Vi star picks out the coefficient of Vi in any vector. And so the value of Vi star on V for all I, those are the components of the vector V, the complete set of components. So specifically, if V is a finite dimensional vector space, and if B is a basis and B star is the dual basis, and I've now written these as ordered bases, any vector V has this form because Vi star of V picks out the coefficient of Vi in the vector V. So this sum gives us V. And in coordinate matrix terms, it may be easier to remember, the B coordinate matrix of V you find by just applying all the dual basis vectors to V. These are the coordinates of the vector V with respect to the basis B. Again, dually, every linear functional on V has this form because f applied to Vi picks out the coefficient of Vi star in F. And in coordinate matrix terms, the coordinate matrix of F with respect to B star is just this column where F is applied to the basis vectors. Well, taking the dual space of a vector space was a lot of fun, you must admit. So there's no reason why we can't do it again. If V is a vector space, then the dual space, V star, is also a vector space. So we can take its dual, which we will denote, as is customary, by V double star. This is called the double dual space of V. It may seem a little confusing at first, so let's talk about what V double star is. Any vector, let's call it phi, in V double star is a linear functional on V star, so it's a linear functional on linear functionals. In other words, phi is a linear map that sends linear functionals on V to scalars. Elements of V star send vectors in V to scalars in a linear fashion. Elements of V double star send linear functionals on V to scalars, also in a linear fashion. So this still may seem a little esoteric at first, but there is one very important and very simple example of members of V double star, and that is evaluation at a vector. So to be specific, if little v is a vector in V, then evaluation at V we'll denote by epsilon sub V takes linear functionals to scalars. Epsilon V of F is simply F at V, F applied to V. Evaluation is linear. You can evaluate a linear combination of functions or functionals at V either before you take the linear combination or after. Doesn't make any difference. So evaluation at V is a linear functional on linear functionals. In other words, these are members of the double dual. So that raises the question, are there any other maps belonging to the double dual space? when V is finite dimensional, the answer is no. And one way to see this is to define a map, eta. This is the Greek letter eta. Kind of looks like an N. It's a very stylized N. This map sends V to V double star. Eta of V is a valuation at V. This map is called the natural map from V to V double star. The natural map is also linear. And in fact, it is injective. Evaluation at V determines V uniquely. And we'll see why that is shortly. So the natural map is an embedding of V into its double dual. In other words, V double star contains an exact copy of V. And what you do simply is a vector V, its copy is evaluation at V. So here are the details. Again, the natural map is an embedding. If V is finite dimensional, then the natural map is also a surjection, so it's an isomorphism. And so V double star it not only contains a copy of V, but it is a copy of V. These two are isomorphic. So the members of V double star are precisely the evaluation maps and no others. To see that the natural map is linear, we just plod through the definition. Natural map applied to a linear combination of vectors. This is a linear functional, F. So the natural map applied to a linear combination of vectors is a member of V double star applied to a linear functional F, is a valuation at this linear combination applied to F, so it's F of this linear combination, and this is where the linearity of F comes in, and we recombine and get this. As to the kernel of the natural map, eta of V is 0, that is to say the evaluation at V is 0, implies that F of V is 0 for all F in V star, and we had a theorem then that tells us that V must be 0. So the kernel of the natural map is trivial. In the finite dimensional case, the dimension of V is equal to the dimension of V star, so V star is finite dimensional, which means these two dimensions are equal. So all these dimensions are equal. The natural map from V to V double star is injective. It maps V to V double star. They both have the same finite dimension. Therefore, the natural map is also surjective and therefore an isomorphism. Okay. So, again, V double star contains an exact copy of V in the form of the evaluation linear functionals. When V is finite dimensional, that is all it contains. when V is not finite dimensional, then the natural map is an injection, but it's not a surjection. So it's not an isomorphism. So there's something else going on in V double star. If V is finite dimensional, there's something else here that's important for me to point out about this theorem. When V is finite dimensional, the dimensions of V and V double star are the same. So we can immediately deduce that V and V double star are isomorphic. Because two vector spaces of any type are isomorphic if and only if they have the same dimension. But that's not the point of this theorem. The point of this theorem is that the natural map is an isomorphism. So while these two spaces are isomorphic because of a simple dimension argument, this is more meaningful to say that this specific map is an isomorphism. So that is the point of this theorem. Because in the finite dimensional case, because of this isomorphism, it's relatively common to identify the vector V and the evaluation, functional evaluation at V. And so to think of the elements of V double star simply as the vectors in V, that's a slight abuse, but it's not uncommon in mathematics to identify isomorphic objects when there is a very strong isomorphism between them, such as the natural map. If we didn't introduce the natural map and we just said, well, in the finite dimensional case, V and V double star have the same dimension, so they're isomorphic, therefore we're going to think of the members of V double star as vectors in V, that would be inappropriate because we don't know anything about the connection between the elements of V and V double star, other than the fact that there is some isomorphism, there is some connection. But here we have a specific isomorphism, the natural map sending little v to evaluation at little v. That makes it more credible to think of those two objects, I guess, as the same or essentially the same.